Welcome to Calculus 1, Chapter 1, Section 1. So what we're going to do throughout Chapter 1 is a quickie review, really, of Pre-Calculus 1 and Pre-Calculus 2. We'll talk about properties of functions, and we'll talk about graphing, not in great depth. We'll be good at graphing once we know more calculus stuff. But you're currently good at graphing certain functions. You're good at graphing lines, no doubt, and maybe parabolas, maybe conic sections in general. So what we'll do is review trig functions in section 3, exponential functions in section 5, logarithmic functions in section 6, and just functions in general in this first section. So really just a recap of Pre-Calculus 1 and Pre-Calculus 2, the greatest hits of Pre-Calculus 1 and 2, with an eye towards what we need in here to do the calculus stuff. Okay, so section 1.1 is on functions and their graphs. So this time, we review several properties of functions and present a number of graphs. So we take these graphs largely as given from what the book is drawn for us. We're not going to do graphing in great depth in this section. We will do graphing in great depth in Calculus 1, but not so much at this stage. So we'll start by assuming you're familiar with the idea of a set, and this set theoretic symbol of is an element of. See the appendix. I'd say please check out Appendix A1 and Appendix A6. Which describe the real numbers axiomatically. A little bit dry in places, no doubt, but it does set up the collection of numbers that we're dealing with throughout calculus. So a function, we'll actually define a function between sets, and then the sets we deal with are usually the sets of real numbers. A function f from a set D to a set Y is a rule that assigns a unique element, f of x and y, to each element x in D. The symbol f represents the function. F is the name of the function. X is the independent variable, and y is the dependent variable, because y is dependent on x through whatever function we're dealing with. The set D of all possible input values is the domain of the function. The set of all values f of x, as x ranges over the domain, is called the range of the function. Domains are usually fairly easy to find for given functions. You throw out bad numbers. What is it you can't do in here? You can't divide by 0. You can't take square roots and negatives. You can't take the tangent of pi halves. We can't take logarithms of 0 or negative numbers. So we have certain algebraic constraints of things that either aren't defined or that we can't do. So finding domains is relatively easy. Finding ranges is actually pretty hard unless you have a graph. And one of the main applications of calculus is to graphing. So questions that ask you to find a range must be either they're going to give you a graph of the function or it's a really, really familiar function to you. But domains, fairly easy to find. Ranges, not so easy to find. Okay, the fact that each number in the domain of f is assigned a unique number in the range implies that a graph will satisfy a vertical line test. That is, if we graph the function, draw any vertical line, a vertical line will intersect the graph of the function in at most one point. Now, it might not intersect it at all. You may be drawing a vertical line that doesn't correspond to a point in the domain of the function, in which case it won't intersect the graph at all. But a vertical line will intersect the graph of a function in at most one point. Now, you may have graphed some stuff other than functions in your mini travels and in your pre-calculus class. You've graphed circles before, I suspect. Circles don't satisfy the vertical line test. Well, then they ain't graphs of functions. So a circle is not the graph of a function. Hyperbolas fail the vertical line test, so a hyperbola is not the graph of a function. There's some examples of things that aren't functions. Now, this thing about domains and what we can and can't do is a little bit of an involved story. When we're looking for domains, usually what you do is you find the bad values of x. What makes it bad? Well, certain algebraic constraints, such as you can't divide by 0. All right, so if you've got a denominator and an x value that could make that denominator 0, that x value is not in the domain of that function. We won't divide by 0. How have I worded this? My colleagues will not divide by 0. You will not divide by 0. Nobody will now or ever divide by 0. It ain't a thing. See the appendices for even more of this. And this will come up again and again, even in the calculus stuff. You don't divide by 0. We're going to deal with limits in chapter 2, and we will go to great length to deal with the fact that, geez, if we're not careful, there's some division by 0, and we can't have that. You can't divide by 0. It's going to look like we're trying to divide by 0. We're not. That's why we're going to the great lengths we'll go when dealing with limits. But nobody can divide by 0. Also, we're restricting our attention to real numbers. So we will not take square roots and negatives. This is a little subtly different from the division by 0 thing. There are people out there taking square roots and negatives, and they're using complex numbers, imaginary numbers, if you like. So there's something different between division by 0 and square roots and negatives. We won't take square roots and negatives in Calculus 1 because I won't let you. We got enough on our plate to not have to worry about complex numbers. It's different with division by 0. There's not some class out there you'll take someday where they finally tell you how to divide by 0. It's not a thing. There is no such thing as division by 0. There is such a thing as square roots and negatives. We just ain't going to deal with it. So we will consider square roots of negatives a disallowed thing in Calculus 1. Logarithms of negatives is a disallowed thing in Calculus 1. You want to use complex numbers? There's a way to take logarithms of negatives. You want to take the inverse sign of a number, say greater than 1? Not going to happen in the real setting. Turns out it happens in the complex setting. Some neat things happen in the complex setting. But our plate is full with dealing with the learning of calculus for real numbers. If you'd like to read more about it, we have a senior, it's a cross-listed senior graduate level class called Complex Variables, in which basically calculus of complex numbers is dealt with. So I've got loads of notes published, posted online concerning complex variables and a number of videos as well. My area of research, in fact, is complex analysis, so I got nothing against complex numbers, but we ain't going to do it in Calculus 1. All right, so that's some of our constraints in terms of finding, say, domains of functions. Let's look at our first example from Chapter 1, going to the supplemental material, where they give us a function, g of x is the square root of x squared minus 3x, and they ask us for the domain and the range. Okay, domain should be not too complicated. Range, that might be a little bit more involved, unless you know how to graph this. And I don't think you know how to graph this. We could maybe get some insight based on your pre-calculus knowledge of what the graph looks like, maybe. This is probably more a question for calculus, and even then it's a little tricky to deal with a graph of this. Well, let's do what we were asked to find about domain first off. Okay, so what's up? What could go wrong? We can't take square roots of negative numbers. Okay, then we need to have that thing under the square root radical to be non-negative. That is, we need x squared minus 3x to be greater than or equal to 0. Let's see what the implication is there. Okay, we'll factor it. as x times x minus 3 greater than or equal to 0. Let's analyze this. I suspect you've done this kind of thing before. One reason I picked this one is you will be doing this kind of thing in the calculus material. I want to basically determine when this function is positive and when it's negative and when it's 0. Well, we can set it equal to 0, x squared minus 3x, that's x times x minus 3, set it equal to 0, and that implies x equals 0 from this factor, or x equals 3 from that factor. Well, now here's a story for this function, x squared minus 3x. Forget the square root stuff briefly. The graph of this, it's second-degree polynomial. The graph is a parabola. Parabolas are continuous functions, so this represents a continuous function. The only way it can change sign, say from positive to negative or negative to positive, is by passing through the value 0. It's a continuous function. It can't get from positive to negative without going through 0. It can't get from negative to positive without going through 0. Some ideas you have about continuity and parabolas from your past, something we'll do more formally in calculus then. So let's see, if the function is 0, if x squared minus 3x is 0 at x equals 0 and x equals 3, well, if it changes sign, then it does it at 0 and 3. It doesn't do it somewhere else. It couldn't go from positive to negative unless it went through 0. The only place that function goes through 0 is when x equals 0 and when x equals 3. So in other words, on the intervals, see the appendices, Appendix A1, I think, has the information on intervals. The interval from negative infinity to 0, that function must always be the same sign. The interval from 0 to 3, that function must always be the same sign. And from 3 to infinity, that function must always be the same sign, that x squared minus 3x function. If it changes from positive to negative, then it does it at 0 or 3. Maybe both, maybe neither, it depends on the function. But it doesn't change sign anywhere else. So it must have the same sign throughout each of these 3 little intervals. So here's what we're going to do. We're going to test the sign of this function x squared minus 3x at test values from each interval. So what we'll do is take the 3 intervals, pick a test value, let's call it k, just to call it something. Pick a number, any number between negative infinity and 0, can't use 0. It's an open interval, so the endpoints are excluded. So let's pick -1. It's a nice clean number and it's in that interval. 0 to 3, pick a number, any number. 1, can't use 0 or 3. They're endpoints and they're not included in the interval. These are open intervals again. 3 to infinity, how about we use 4? We'll plug those numbers into this function. Let's call it f of x. We're using g to indicate the original function. This is a piece of the g function in a sense. So we'll take x squared minus 3x and plug into it these 3 values. Plug -1 in, we get -1 squared minus 3 times -1. That's 1 plus 3 is 4. And the important thing about 4 is it's positive. Remember, the sign of this function is going to be the same throughout that interval. So I pick any number in that interval, plug it in. Whatever I get out, looks like it'll always be positive. I plug in a number, I get out a positive. No matter what number I plug in from that interval, we'll get out a positive. That's because that function is positive throughout that interval. It's got the same sign throughout this interval too. All I got to do is figure out what that sign is by picking a test value. Let's use 1. Plug 1 into the function, we get 1 squared minus 3 times 1. That's 1 minus 3 is -2. Is negative is the part that matters. The function's negative throughout that interval. Pick a number, any number, a test value from 3 to infinity. Let's use 4. Looks like we get positive 4 out there. I suspect there's some sort of symmetry going on here. Anyhow, that's positive, and so the function is positive throughout that interval. So we've got the function is positive on this interval, negative infinity to 0, and this interval, 3 to infinity. Ooh, it's negative from 0 to 3. We can't have that. Remember, what we're doing is trying to avoid the squares and negatives. Okay, so we'll carry that information to the next slide. The good part was negative infinity to 0 and 3 to infinity. So we get x squared minus 3x greater than 0 for x between negative infinity and 0, or between 3 and infinity, unioning together those intervals. If this set theoretic notation and this interval notation bugs you, please read through and watch the video on the Appendix A1. We're going to be using interval notation a lot. But that was strictly greater than. We can't take the square root of 0, so we can consider greater than or equal to 0. We looked at the strict inequality so we could make that table and do the test values thing. So it's okay to include where the function was 0, which was at 0 and 3, so I put little square brackets on there. We don't have a problem. We'd be taking the square root of 0, which is 0, no problem there. It's a square, it's a negative, so it causes problem. So for these x values, the thing under the radical is non-negative. So that represents the domain of g, g being the square root of this quantity x squared minus 3x. So domain, there it is. And we found it by looking for bad things. Bad things were square roots and negatives. We threw those out effectively. Other bad things are division by 0. We didn't have any division, so that's not an issue in this one. I'm sure it is in some of the other exercises. Other things, more of this later, but the tangent of pi halves, the tangent of negative pi halves, logs of negatives, log of 0. Some of the other trig functions are undefined in certain points. So these are the things that can go wrong, and these are the things that may go wrong in Calculus 1, because we're only going to consider these algebraic functions, logs, exponentials, and trig functions. Okay, that takes care of the domain. Oh, dude, they wanted the range as well. Okay, that one's a little more complicated conceptually. I mean, the computations aren't so long. But suppose R is in the range of G, and choose this R to represent a range element. That means R equals x squared minus 3x square root of for some x in the domain of that function, some x up here. Okay, first off, if R is the square root of something, then R is non-negative. Please read Appendix A1. Square roots. The square root symbol represents the non-negative square root. So when you write square root of something, you're not getting the negatives out. You're getting the positive square root out. That's just what the symbols mean. So what's coming out of this function g? Well, it's square root of something or other. So when you get things out of the function, they will be non-negative things, because square roots, the square root symbol, always gives you a non-negative square root. It's mentioned in the appendix, the idea of what's the square root of 9? Square root of 9 is 3. It's not plus or minus 3. Plus or minus the square root of 9 is plus or minus 3. You ask your calculator for the square root of 9, it's going to tell you 3. It ain't going to tell you plus or minus 3. You only get non-negative values out of square root functions. So this r that comes out of the square root function must be greater than or equal to 0. It must be non-negative.